It's really my pleasure to introduce Dr. Yang Yi from the Jet Propulsion Lab. Yang and I have known one another for probably decades, even though she doesn't look like she could know me for that long. And today she's going to speak on unraveling lunar volcanic gases, a peek through the samples. Yang, it's all yours.
All right. Thank you, Chief, and thank you for the opportunity to talk about our recent results. And I think belatedly, I realized today is Valentine's Day, so I wish everyone on the telecom a happy Valentine. The title of the talk changed a little bit from the announcement. I thought this is a great opportunity to talk about our research regarding finding ways to constrain the lunar volcanic gas. Okay, without further ado, let me move on. I'm always guilty of running out of time, so I want to make sure I acknowledge my colleagues before I run out of time. So the research I presented here today cannot be possible without the great work from my colleagues. So here I listed people involved with the data I'm going to present in the talk today. I want to mention that Ms. Xue Su is a graduate student at the University of Michigan. She is the heavy lifter for one of the results I'm presenting here. All right, so we know for a long time that since probably before, when the sample comes back from Apollo missions, that we have evidence of volcanic volatiles on the moon. And this is mainly recorded by volcanic glass beads that produced by pyroclastic eruptions. And we also have volatile rich basalt, such as vesicular basalt. Those are lava flows, volcanic rocks. So we do have evidence of the volcanic volatiles. But our understanding of what the volatile is made of has changed throughout the time. So when the sample comes back through the sample analysis, we know that volcanic beads contain measurable or detectable sulfur. We also know the surface of the volcanic beads are enriched in volatile elements. But our understanding has taken a drastic change, revolution in 2008. We, through landmark papers such as Alberto Sal's work, we recognize that there are residual hydrogen, fluorine, chlorine in volcanic glass beads. Additionally, with subsequent work, we also realized there are abundant hydrogen in olivine-hosted melting inclusions that is associated with the orange glass beads. And from that study, we can roughly infer that the lunar mantle associated with the orange bead eruption can contain significant amount of water that's comparable to terrestrial morph mantle. We also have evidence from minerals such as apatite or plagioclase. Subsequently, we also confirmed, we means the community, confirmed that there is carbon, residual carbon in volcanic glass beads. So from those studies, we know that lunar volatile budget is made mainly by hydrogen, carbon, oxygen, and sulfur, with minor amounts of sodium, potassium, zinc, and a trace amount of other volatile elements. However, even with these findings in the last 10 years, or slightly over 10 years, we also recognize there are some discrepancies. So I think the current debate or current unanswered question is still whether the moon is wet or dry. So from the previous slide, from the high hydrogen amount in melting inclusions, it shows that some of the lunar mantle sources could be right. But at the same time, when we look at isotopes of metal volatiles, such as zinc, chlorine, gallium, and rubidium, of marine basalt and some plutonic magmatic samples, we recognize those samples are enriched in heavy isotopes of those elements. So here are two examples. I use the right vertical bar to show where the terrestrial value would have been. And in comparison to the right bar, we see that some lunar basalts are enriched in heavy isotopes. Some plutonics are enriched in heavy isotopes. And this kind of wider occurring enrichment of heavy isotopes suggesting these samples or their mantle sources experienced volatile loss. So which would have suggested a dry lunar mantle. So the conventional explanation for this volatile loss, is that those metal volatiles, zinc, iron, or other metals, are lost by in the form of metal chloride. However, is this really the case? Because through the studies of returned Apollo samples, we have never really confirmed presence of metal chlorides in the samples. There was one finding of sodium chloride, and that's it. And most of the studies previously inferred what are the vapor species based on the chemistry. So in order to address this missing link, like how does lunar magma alter gas, we decided to look at the volcanic eruption products, such as the volcanic beads and the vesicular basalt, where we know they have condensed vapor. So the methods we use are typical macro beam analysis instruments that are shown here. We also include other methods such as X-ray computed tomography or laser ablation ICT mass spec when we have specific questions we want to answer. Okay, so first let's look at our studies of volcanic beads. So from Apollo era, we know there are different volcanic beads, different chemistries that are erupted from different mantle sources. So in this plot I borrowed from Eric Horry's paper, I think this shows the color relationship with chemistry clearly. So as you can see, we have green, yellow, orange, black, or red. They are mostly different based on, because of their titanium oxide content. So we know the moon is really, the surface of the moon is a very harsh environment, very reducing and a very high vacuum. So in our study, we time our observation in order to document any changes by terrestrial environment. And for our studies, we tried to avoid using any liquid in our sample preparation because from the vapor condensates from the moon, we suspect they are really highly reactive. So, so here are some examples, and I want to call out that we recently was allocated a sample from 73001. This is a black bead cloud that was part of the sample that was opened by ANGUSA program, which Chief is spearheading that effort. And we obtained a small amount of sample from that cloud. This is perhaps the most fresh sample we have because it has been sealed in vacuum for the last 50 years until 2022. So the first study we did is looking at the surface of the beads. And those are group of us that's involved in that study. So basically here is an example comparing the secondary electron versus backscatter electron images. So secondary electron images give us mostly the topography, like bright features are usually higher relief compared to darker features. On the other hand, the backscattered electron image gives us more average composition information. So when something is brighter in BSE, it's denser, heavier in terms of its average atomic number compared to darker material in BSE. So in the subsequent slides, all the images would have been backscattered electron image unless specifically noted. Okay, so the first discovery we encountered is for orange beads. So on the right side, right-hand upper right corner, I put a circle to indicate what type of glass beads we found the features in. So it was a bit surprising when we were observing the orange beads. We see actually the surface was contains contains two types of salts or phases. So one type is a zinc-rich salt, and they occur in this kind of triangular shape, suggesting a trigonal crystal structure. We also have seen rods that are darker, that enriched in sodium. And the distribution of those two phases are quite widespreading. So this is an example of a bead. So if you look at the left-hand side, we have the zinc-rich phase actually quite in a high number density on the surface of this bead. And there is a cluster over here as well. So when we look at the chemistry of those two phases with SEM EDS, we see that the zinc phase, of course, you know, we tried the different voltages in order to confirm the zinc is present in that bright phase. So we use the SEM EDS to constrain the chemistry. Because although those are bigger, like micron-sized grains, they are very thin. So we use different excitation energies to minimize the contamination from the substrate underlying the phases. So with a constrained chemistry, we can infer that the zinc phase is so the red curve in this plot, the zinc phase is the zinc phase contains high zinc, high chlorine, also high sulfur, as well as some sodium here as well. For the sodium phase, which is a blue filled curve, that one contains only sodium, potassium, and sulfur, no chlorine. So we use the elemental chemistry to infer the precursor phases. So the reason for that is Apollo 17 orange beads were collected on the moon, but not sealed in vacuum. And those samples are stored in the airlock on the surface lunar module that experience depression and repressurizing cycles. So the samples have seen the cabin air on the lunar surface. So the sodium salt and the zinc salt are altered products from the condensate. Because we didn't use water or any other liquid, the elemental chemistry such as sodium, sulfur, or zinc to other elements, except for oxygen, we believe those ratios are kept. So we can use the elemental chemistry to infer what are the precursor phases. So with that information, we derived that the sodium salt is actually a sodium potassium sulfide, and the zinc salt is mostly zinc metal with a very minor amount of sodium, chlorine, and sulfur. So even if we assign all sodium to chlorine or sulfur, zinc to chlorine and sulfur, there is excess zinc to that can only be explained as zinc metal. Also, from the ICM observation, we can look at the texture between the sodium and the zinc salt. From the images shown here, as you can see, the zinc salt lies on top of the sodium one, which is suggesting the sodium sulfide was deposited first before zinc formed. We looked at the 45 beads. About 80% of the beads contain this sodium potassium salt, while only 50% contain zinc salt. So this is one discovery for orange bead, the first discovery. And last year at LPSC, my colleague Chima presented our discovery of zinc sulfide nanocrystals on the surface. So the example shown was a yellow bead, but we have confirmed the zinc sulfide presence on 4 types of different beads. So here is example of zoomed out image of the surface of the bead and zoom in. So I borrowed this slide from Chu's presentation last year. And as you can see, when we keep zooming in, we see the nanometer size zinc sulfide coating on this yellow bead. And it seems to be a very uniform coating for this bead. The size ranges about 20 to 70 nanometers for when we included all other bead observations. The chemistry of the zinc sulfide is inferred again with the low voltage EDS analysis. So we see a roughly zinc to sulfur ratio, molar ratio about 1:1. So coming back to 73001-226, the black bead, we just an example of the type of zinc sulfide we observed. So here is the image of the whole bead, and we're going to look at the area outlined by yellow box. So zooming in again. Now we're at 50,000 times magnification. You see those little subangular greens. Those are zinc sulfide bases. So we can compare the chemistry. Sorry about the fuzzy images. So the EDS spectrum, we can compare the area with and without these little greens. And as you can see, we detect enhanced zinc and sulfur content when we compare those two different regions. Okay, so third discovery, this is going to be presented at LPSC this year by Chu on Tuesday afternoon. So third discovery is iron sulfide and iron nanocrystals on, actually I should change the title, on yellow glass teeth. So for this study, we looked at three yellow beads so far. So here is an overall look of the outside the surface. This is a fragment of a bead, but we can see the outside the curved surface. So here is the zoom in on an area of the bead, and over here is more high mag images to show the crystalline deposit. So we see this is more like a larger iron nano grains and also smaller ones. We also see that the coating of iron sulfide has different sizes. So Chu will present more details at the LPSC in a few weeks. Okay, discovery 4. This is the sodium chloride discovery that was in the original talk. We looked at the 9 beads from this sample, and here is the only bead that we observed the sodium chloride. So here is the overall image, and we are looking at 2 different areas In the abstract, we said we only found in this kind of depression area. And now with further observations, we actually see the sodium chloride widespread on this bead rather than just confined in one area. So here we look at the green area over here. This is a secondary electron image. So now let's zoom in. This is a zoom in image of the green area. And you see the sodium chloride occurs a little bit sparsely. So this is also slightly different from the LPSC abstract. This will be a poster presentation at LPSC. We see zinc sulfide as well as sodium chloride. And we see beautiful cube-shaped sodium chloride on a fractured surface. So as most of you know, sodium chloride under electron beam may not be stable. So we also timed our observation. We prepared the sample like within 30 minutes and conducted the observation. We came back to look at the sample 7 hours later. Nothing changed. Then we checked again 2 months later. So as you can see from the dates here, it's about 2 months later, and the green still there, but it is very beam sensitive. So sorry, the magnification here is slightly different, but the shape, the size of the sodium chloride didn't change over 2 months. Okay, as a summary of the surface observation, we see ubiquitous nanometer-sized zinc sulfide on different beads, suggesting zinc sulfide is a common deposit from volcanic gas. For all other observations, they are somewhat limited to spatial chemistry, but some of the work are ongoing, we expect to give an update later. But just want to emphasize that sodium, potassium sulfide, and also zinc metal are not common, but they are common on orange beads and black beads. Okay, so how do we incorporate the data? So there are few papers published in terms of modeling zinc and other metal volatile species in lunar volcanic gas. So Rundley et al. 2017 published the modeling using assuming a equilibrium gas solid species at a given temperature, pressure, and oxygen fugacity. The plot, you don't have to, there is no time to go into the detail for the plot, but basically the figure generated on the top here is to show in terms of at the certain temperature, pressure for that element, would that be in solid phase or gas phase? But this doesn't tell you for this figure what species it would have been in. Rather, you use a plot on the bottom like this to show whether it's a zinc sulfide or zinc metal. But as you can see from both of these models, zinc is predicted to be mostly in zinc sulfide, but not zinc metal. So the observation of zinc metal still not explained by current models. Mikhail and I are also performing gas modeling in order to understand the formation of sodium potassium sulfide. So this is ongoing work, and we can generate sodium sulfide, but the gas chemistry is key here. So take home one for this work. We see some fundamental differences in terms of gas condensates among different volcanic beads. This is suggesting the volcanic gas can be very different among different eruptions. This is actually also agreeing with what was reported for volatiles inside the volcanic beads. Orange and green beads have very different volatile concentrations. The way of the volatile metal outgas from the lunar magma, rather as chlorides, they actually go through processes involving multiple reactions. So for example, like sodium in the silicon melt, it would first be outgassed as a metal phase. So dissociation with the oxygen bond in the melt, so is sulfur. and then those native state elements in the volcanic gas will react and then form the solid precipitates. So this also has implications when we do isotope modeling in terms of how the isotope would evolve, because it's not a same species type of modeling. Okay, so now let's look at the interior of the bead. As I mentioned before, this work is mainly done by the graduate student at the University of Michigan. And so this is image of the interior of an orange bead. It's really glassy, homogeneous with no microlights. So before our study and in the excellent work by Alberto Saul et al., they analyzed volatiles inside the beads with seams. And those are usually done by placing the seams spot in the center of the bead. Only one green bead in Saul et al. 2008 shows outgassing profile of volatiles. But if you examine the figures, the analysis stopped at 10 to 20 micron-ish from the edge. So it didn't go all the way to near edge. When we looked at the samples with microprobe, we saw that the sodium oxide actually shows an increased trend toward the edge of the bead. So here are 4 plots from Su et al. 2023 paper. Orange lines are the physical boundary, the edge of the beads. The gray symbols are EPMA data, electron probe data, and the red symbols are SIMS data, and the blue symbols are extracted from laser ablation ICP mass spec mappings. So we first recognize the trend from electron probe analysis because there are potential secondary fluorescence effect and activation volume of the beam. We verified the trend using different techniques like SIMS and laser ablation ICP mass spec. What this profile shows is that the bead likely started with a higher sodium content. During the eruption, it lost some of the initial sodium in the bead, and then toward the edge, we see sodium diffuse back into the sample. So in addition to sodium, we confirm this kind of in-gassing trend exists for potassium and copper. So here is example of laser ablation ICP mass spec mappings of one bead, and this is also confirmed for green bead. This was reported, I think, by Su et al. 2022 at AGU abstract. In addition to the metal volatiles, we see sulfur in-gassing. This is going to be presented by Xue at LPSC in the same session on Tuesday afternoon. So I'm not going to go into details here. She will be giving more details at that talk. Just to recuperate a little bit why we see this kind of review a bit why we see this in-gassing trend. So the solubility of volatiles is a temperature-dependent function. So when we first erupt at a higher temperature, the dissolved sodium is higher than the sodium in the ambient gas. So we see outgassing of sodium. But when the temperature cools, the pressure in the ambient gas is actually higher than what we have in the melt or in the glass bead. So we see this kind of diffusion back into the bead. And Xue created this fabulous diffusion model, and we can actually model this kind of outgassing and in-gassing trend with just a single equation and 3 unknowns. The unknowns include this cooling timescale, and also a kind of empirical function for solubility. So the unknowns are A sub 0, B sub 0, and tau. So for each element, we have a single pair of A sub 0 and B sub 0, but for each bead, we model for one single tau. So we performed those modelings, and we can obtain the cooling rate for each of the beads. So here is take home 2. From the individual bead concentration profile study, we can constrain the cooling rate of each bead. We also can generate empirical equations for sodium copper solubility. We only model the sodium copper because we only have diffusivities for those two elements. This is a new behavior that has not been recognized before. Together with our surface observation, we think the volcanic gas has enough time and also enough density to allow those behaviors to occur. So that's our second part of the volcanic beads. Now moving on to the third part of the talk. This is a study of lunar vesicular basalt, and this is the work done by myself, Chu, and also Scott, who is online. So the samples we studied first, and we're looking at more samples, is a highly vesicular basalt 15556. This sample was collected by during EVA-3 by Apollo 15 astronauts, and it's collected very close to the Hadley Rail, which is considered to be a lava flow channel or collapsed lava tube. And on the wall, we can see stratigraphy layers suggesting it's similar to terrestrial inflated basaltic flow. The sample we looked at is actually a very small chip coming out of this subsample 2 to 3. We also have 2 thin sections also collected, made from this rock in order to compare what we see in 3D with 2D data. Okay, so here is first discovery. We found copper sulfide on pyrrhotite in this sample. I think copper sulfide has never been reported before in lunar samples. And the occurrence of the copper sulfide is very ubiquitous. So all the sulfides we see in the sample has more or less been coated by copper sulfide. So here is one example. This is optical image of 2 sulfide grains that's sitting on the vesicle wall. So now you're looking down the vesicle at the vesicle wall, seeing the pyrrhotite grains, euhedral large grains sitting on the vesicle wall. Okay, zoom in. This is the bottom grain, and you see those copper sulfide coatings. There are multiple coatings. There is 1, 2, 3 over here, and you also see there are flow lobate. So the coatings seems to be following this pattern that suggesting some kind of flow. And zooming again, and those copper sulfide can be really nanocrystalline or slightly larger. Some of them have this kind of bladed morphology, and some of them seem to be amorphous, not amorphous, but clumps of multiple grains. We also see an iron metal grain protruding from the iron sulfide grain too, but this is not always the case. In this case, we do have an iron metal grain. This is another example. This is my favorite example because here is a large pyrrhotite grain. And when we zoom in this area, we see that this grain is coated by copper sulfide. So you see the fine grain coating. At the edge of the coating, we see copper sulfide rosettes. They are actually almost resembling they're resembling in terms of the texture as desert rose, but much smaller, a few microns across. We also see discrete copper sulfide grains that forms this kind of linear pattern on the surface on top of the coating. This is another example. Including this example is mainly to show the EDS chemistry of the copper sulfide coating. So it's pretty pure. We don't see nickel or cobalt or even iron associated with those copper sulfide coatings. In order to check and whether what happened with the iron sulfide grain, we searched and looked for the cross-section of iron sulfide on the vesicle wall in the 2D section. So several things to note here. We don't really see alteration of the iron of the pyrrhotite grain in the cross-section. There are cracks and fractures which are possibly generated during sample preparation. We do have a hint of enriched copper when we put our electron beam at the edge of this pyrrhotite grain. And the pyrrhotite grain is actually not just sitting on the vesicle wall. There are roots of the iron sulfide grain that kind of irregular shaped going into the rock. Although the outside profile looks very unusual, but we do see things kind of going into the rock, extruding into the rock. And it also has a lot of iron metal grains. And the iron metal grains helps us to understand the formation of the iron sulfide as well. In addition to seeing the copper sulfide on vesicle, on the iron sulfide on vesicle walls, we also found copper sulfide on the fractured surface of iron pyrrhotite inside of the rock. So here is an overview of the chip we observed. There are abundant vesicles. There are two sulfide grains over here, one clearly on the vesicle wall, one is slightly recessed. And we are going to look at this area, which is between two vesicles. So, oh, sorry about that. Oh, sorry about the blue box. Should have forgot to change. So here is a zoomed in image of that region. Over here is a continued zooming in image of that pyrrhotite grain inside the rock matrix. This is a fractured surface. So we got the chip as is, and this is on the surface that was chipped off. On the surface of the fractured plane, we see a copper sulfide again, coatings along those fractured surface. The pyrrhotite in the matrix appears to be altered, but we didn't really see the alteration products such as, for example, metal iron, as we would have expected from the alteration of pyrrhotite, but it does seem to be following these porous channels. There are channels through the pyrrhotite. So I want to show you this example as well, but as a summary, for this sample, it's actually very stunning because here is a fracture on the pyrrhotite, the wall pyrrhotite, but we see these coatings, multiple coatings again, one very fine-grained, another one, second one, and then in the center, there seems to be the last part of this copper sulfide material. And for this one, you know, most people on the call probably can resonate with this image because if you drop a coffee drop on table, when it dries, it looks like this pattern. But I'm not saying this has to be that way to form, but it does show some kind of fluid that's coming out and depositing the copper sulfide. So take-home summary for copper sulfide discovery is copper sulfide is quite pure in terms of chemistry, no nickel or cobalt associated with the copper sulfide grains. Nickel, cobalt are both chalcophile, sulfur-loving elements, so we don't really see that here. Copper sulfide occurs as in different forms, but often together in each individual occurrences. In terms of the formation of the copper sulfide, I think we can, we are confident this is more formed through low viscosity fluid. Fluid can be a dense gas form. It doesn't have to be liquid form, but a higher density gas. So whether this is gas deposit or gas solid reaction or gas fluid remobilization of something, that's up to debate. But right now, the evidence appears to be leaning toward some kind of remobilization process. Okay, discovery 2 on the same sample. I'm only showing a few images, but we have very high quality images deposited on the open access server. It's a draft paper, so don't take the interpretation or discussion of the paper seriously, because we're revising the paper based on the reviews we got. But when you look at the images here, what you're seeing are, again, you're looking down the vesicle, and those are holes on the vesicle. So there are holes connecting the vesicle to the rock matrix. I always nickname the left-hand side as a hairball texture. So it's like a hairball down the drain. The right-hand side is different. It's more like fluoroapatite straws formed in cluster form. In both cases, we do not see abundant silicate minerals associated with fluoroapatite needles. There are small amounts of other minerals, but not silicate minerals. And so far, we observed 2 cases on vesicle walls for this sample. We studied like 4 different chips, several different vesicle walls. So here is the zoom in. The left-hand side is a secondary electron image. As you can see, the fluoroapatite needles are climbing up out the hole in the vesicle wall, and some of those are actually protruding to the empty space. I didn't show the whole area, but they follow this kind of flow pattern around this hole. On the right-hand side shows the empty center of those fluoroapatite needles. And to show their chemistry, this is not a clean analysis again, because it's a very small grain. But as you can see, it's a calcium phosphorus fluorine. Chlorine is really low. So it's mostly a fluoroapatite. In order to constrain the chemistry, again, we look at the 2D sections in order to help us to understand how the minerals on the vesicle wall are related to the rock itself. So over here is one of the probably most close example of the vesicle pile. Sorry, the needle piles on the vesicle wall. It's not the same.
What's wrong with you? There.
Oh, sorry, I think someone needs to mute. All right, so over here, those moderate gray shaped needles, those are fluoroapatite. And the 2D sections, you can see they have empty centers, but they are clusters. So here are 2 vesicles, and but we see the apatite needles wrapping around the vesicles and integral with both phyolite and glass, and also pressure clays. So it's intimately grown in this area we call later stage metastasis with different minerals. So it's suggesting their formation is not really depending on the exact chemistry of the melt they are associated with. They occur almost probably not same time, but in different melt as probably, quickly. So we also compared the chemistry of the needles with fluoroapatite that are in the matrix, but away from the vesicles. We do see this kind of evolution trend in terms of dropping fluorine, but higher total rare earth element and the yttrium content. It's suggesting the melt they grow out of are highly more evolved, more fractionated. So as a summary, we think those floral appetite needles are non-equilibrium growth out of the latest stage melt. And then the final stage melt was probably pulled towards the vesicle because the vesicle would have lower pressure than the equilibrium pressure inside the rock. So when it was pulled towards the vesicle, those needles quickly formed and formed this kind of pattern. I think this morphology has not been recorded before, so it's interesting to see what happens when the lunar basaltic lava almost fully solidified. There are a lot of things happening, which is kind of eye-opening in terms of that. So take-home message 3, for our observation of vesicular basalt, we have seen different textures and the new occurrence of minerals that have not been reported before. And their formations are closely related to the final stage fluid and lava activities. And our understanding of that is highly limited because there are no similar experiments we can use from terrestrial literature to explain our findings. Many of the even the theoretical models are limited. So, but I think there is a lot to be done here, and I want to use the left-hand side image to show that, you know, when the lava, basaltic lava erupted, extruded on the surface of the moon, it can grow to a huge, a large thickness. If it's volatile rich, it may be like terrestrial lava as well, that it will have vesicle-rich zone, but the center and cooled fat earlier than the center of the lava flow. The center of the lava flow will be volatile rich and warm. So we have a temperature pressure gradient that will help the volatile to move from the center of the lava flow to the vesicular region, cold region of the lava flow. So there may be some volcanic gas fluid activities associated with that. So those are thinkings that still evolving, and I think with more observations, we'll be able to understand it better. So as a summary, I think there are a lot of things I kind of crammed into this talk, but I want to emphasize a few things. One, return samples are a gift kept ongoing. Sample return is important. We still have so much to understand from the moon, and future return sample from Mars will likely revolutionize our current knowledge of the planet or planetary bodies. So I'm going to leave you this fabulous video that was made by Scott, and we're trying to show the relationship of the sulfide, the pyrrhotite metal, and the different vesicles. So thank you for your attention.
Thank you very much. That was an intriguing talk, and you're showing some really great results. I look forward to your talk at LPSC.
Me too, but I didn't know.
Before we take additional questions, I just want to make sure that everyone, I just want to announce that next week's speaker is Justin Simon, who will speak about felsic magmatism on the moon and the role of volatiles in their petrogenesis. So can we take questions for Yang? Any questions here? Ricky, do you have any questions online?
I'll ask a question. This is Francis.
Yep, go ahead, please.
So Yang, you talked a little bit about it, but could you give more insights into where you think the copper might be coming from?
Yeah, thank you, Francis. That's a great question. That's what is puzzling because I think overall copper content in this specific sample is like 26 ppm. And we're seeing copper sulfide with copper content like 40% each. So there has to be a way to enrich copper and separate the copper from nickel, cobalt, which are also, sulfur-loving elements. So we think, well, copper is probably more volatile than nickel, cobalt. So that may be a way of enriching copper. Another way maybe when we have basaltic magma cooling, when there is sufficient sulfur, we can reach monosulfide saturation early during the formation of cooling crystallization of the lunar basalt. And that monosulfide solution will take most of the nickel, cobalt, and copper in the magma into the sulfide. And that sulfide melt will further cool and separate into iron metal and iron sulfide. So that can be another way of separating copper from nickel and cobalt. So both are possible viable processes. Either copper was condensed early by volcanic gas and then remobilized and reconcentrated on the vesicle walls, or it can be somehow extracted from the iron sulfide part of the sulfide melt. The sulfide we see in the rock matrix, where on the fracture surface we see those copper sulfide, appears to be suggesting there's some kind of mobility of whatever deposited the copper sulfide. So, it's just there are not enough experiments done to help us to say, hey, it has to be this process.
Sounds like there's a lot to do. That's exciting. Thank you, Yang. Very nice talk.
Penny King, do you have a question?
Yes. Lovely talk, Yang. I really enjoyed it, and just so beautiful. The images you have are gorgeous. I had a question about that cross section with the pyrrhotite going into the sample.
Oh, sorry, here.
Yeah, that one. I was wondering what you think that's doing in 3 dimensions, and whether it's maybe going into some of the cracks and holes in the wall.
Mm-hmm. Yeah, I think it seems to be following along a pathway, and in the root we do see also appears to have some holes. The Apollo 15 556 is actually, the vesicles are 30 to 40 volume %, but the porosity is actually pretty high. That's shown in that CT scan. And with the CT data, we see for some of the sulfide, not just this 2D section, in our chips, there are roots that are going from exposed in the vesicle to the rock. So it suggests some kind of ductile behavior of the sulfide. I don't know whether there is also a pressure issue here, because in the second to the last slide, we see the lava flow structure. So if the vesicular basalt was exposed under vacuum, there will be pressure gradient between the vesicle and then the rock itself. So maybe there are some additional movement caused by this pressure gradient between the vesicle and the rock itself. So perhaps there are flows. I'm not certain.
No, it's interesting.
Yeah, and the other
Yeah.
thing I want to use this to emphasize to show is there are suggestions that some of those wall periodite could be vapor deposit, like just deposited out of the vapor. And we already show that on glass beads we can have iron sulfide. To me, for a vesicular basalt, it may not be the way the wall periodite formed, because we see this kind of connection with the rock itself.
Yeah. Okay. Thanks very much. Really interesting.
Great,
Yeah,
thank you,
thank
Penny.
you.
We have time for one more question. I don't see any out there. Well, I do have one, Yang. This is
Sure.
Chip. The pyroclastic deposit that was sampled at Station 4 of Apollo 17, that's 74001, 74002, seemed to have, people have suggested texturally, or the stratigraphy suggests a change in eruptive style. Could you predict how the volatile coatings could potentially change during changes in eruptive style? Or is that something that you still would like to really investigate?
Very good question. I don't know if I can predict. I think the database right now is very slim. As we build the database, we'll know better what happens with each different eruptions. But 74220 is more like an orange light, 7400 deposits are similar to, in chemistry, to the orange bead we studied. So, and it's also very interesting that we only found sodium chloride with black bead. We found one, and Clinton and our 1978 studied the 74220 samples, and they only found 3 beads with sodium chloride. So that possibly may be the difference we're looking at, and we do need more studies, I think. So that would be the next samples to examine carefully to see what are the vapor products, and whether with additional modeling to understand whether the volatile chemistry changed.
Great, that's terrific. Thank you very much. And we're going to be ending up on time. So you did a great job too.
Yeah, thank you, Chief, for the opportunity. Thank you for everyone for being here.
Yeah, and I just want to thank everyone for joining us. Thank you again, and hopefully we'll see you all next week. Bye-bye.